The last class, we covered the topic of metals. We talked about, I believe, displacement reactions, identifying metal ions, the extraction of metals, the extraction of iron in particular, and then corrosion of metals, focusing on rusting, and then how rusting is prevented via different methods like painting or oiling, coating with plastic, galvanizing, and sacrificial protection. So we just have a bit of the topic left, which we will cover and then move on to our next chapter. So under the topic of corrosion, we are basically talking about rusting, as we just saw. And so let's talk about corrosion of other metals. And so the thing is that the corrosion of other metals is right. So rusting is the most common form of corrosion, but the term rusting is only used for iron. For iron and steel. What about the corrosion of other metals? Well, they do react with oxygen in the air, they do react with water. So with oxygen, water, and other substances, obviously. But that is not called rusting, it's just called corrosion. And obviously, right, how quickly and to what extent of their corrosion depends on their place where in the reactive
And
process.
the yeah.
So what happens, right? Sodium, potassium aren't used for general work. They're stored under oil. They're super reactive, right? So we don't really talk about those, but we have seen a video as well last time that as soon as you take sodium out, it immediately reacts with the air. It immediately forms a layer on top, right? That's how fast it is. Uh, right. Same thing. They give the example of magnesium, calcium, and aluminum. Adjust the grid lines. It's okay. So magnesium, what is that? Calcium and aluminium, right? They react with oxygen and form a thin oxide layer on the surface. Right, and in case of aluminum, we've talked about it that the oxide layer actually makes it less reactive. And because of that, it has a wide variety of uses. Plus the fact that it is less dense and lightweight compared to other metals. right? Copper, for example, if you've ever seen copper, have you? It's actually pink,
Okay.
but you might have seen copper being brownish, and that is
Is it
because
like rose gold type?
kind of maybe, right?
Okay.
But on exposure to uh, air, so when it's exposed to air, right, it quickly turns brown, right, on the surface, and that is because copper 2 oxide is found.
Okay.
Copper 2 oxide. Then, right, in certain environments, copper becomes covered with verdigris. It's an I, should be an I. Let's rewrite the whole thing better. So, word, okay. And this is green in color, right? And it is formed of, copper salts. So, right, the copper 2 salts include copper carbonate, or to be specific, copper 2 carbonate, and copper 2 hydroxide. So what it looks like is this. You got CuCO3, CuOH2. Alright, so you got two different copper, got copper hydroxide and copper carbonate together in this verdigris, right? Perhaps some others as well. And as we know, gold, silver, platinum, they're unreactive. They do not corrode even after a very long time. Any questions?
No.
Okay. And lastly, for this chapter, alloys. What are alloys? They are, a mixture of metal. Remember, mixture
Okay.
of a metal with other substances, right? Which may be other metals or non-metals. Depends, right? And so what happens when you produce alloys of metals is that they have sort of more enhanced properties, more enhanced useful properties than the metal itself. Which metal? The one that you use. This guy. Into which you mixed other things. So, right, let's say then the pure metal itself. So an example of an alloy is brass. Right, which is made of copper plus zinc. Right, it is harder and more corrosion resistant. Harder and more corrosion resistant than either of the metals. Right, and it is used an example, plumbing and let's say plumbing fixtures. Right, so good quality plumbing fixtures like your faucets on your wash basins and kitchen sink and some of the pipes used in plumbing. Not nowadays now they've shifted to PVC, but older pipes, but at least the faucets and the external fixtures, the good ones use brass. Why do they use brass? Because, right, they don't corrode. And so, right, they last a very long time, they have good performance, and they're made of metal, so they're also very resistant to wear and tear. Right, you're opening and closing the tap and everything, and so it won't break or spoil easily. Right, you'll actually have to wrestle with it to break it somehow.
Yeah.
Right, you've tried wrestling with it.
No.
Then you've got stainless steel, which you hear about a lot. So brass is an example. Another example is stainless steel, and this is iron. Right, plus, well, actually you got steel. So steel is produced, and then you've got, right, maybe chromium or nickel. And so what chromium does, it prevents from rusting. And so again, right, bathroom fixtures or faucets, the silvery faucets that you use, right, the stainless steel faucets or fixtures or stuff like that that you may use around water, and they don't rust. That's why, right?
Okay.
And nickel makes the steel harder.
What is a nickel?
Nickel is an element, right?
Okay.
Nickel is an element, and its symbol, if I can just find it, I believe it's, well, obviously it starts with an N, and I believe, yes, Ni. So it's element number 28.
Okay.
Nickel, and chromium is Cr. Right?
Yeah.
And Okay. So today, right, many different alloys are made depending on requirement. Right, so there are people called metallurgists. They're called what now?
Metallurgists.
Yes, metallurg.
I didn't guess they make metals.
They can't make metals. They
Oh,
work.
sorry.
They work with
Yeah,
metals.
the metal.
Right, and so they design alloys to suit whatever particular need you have. So they make, right, tailor-made alloys. All right, you want them harder, you want them stronger, you want them more corrosion resistant, etc., etc. Right, depending on what it is that you want. Now, what happens to the particles of a metal? Why does it become stronger? So we know that this is what metals look like. Right, we'll do this a bit smaller, and right, this is how particles are arranged in a metal. What happens when you make an alloy? Draw this. And then you've got this guy sitting over here, and maybe another over here. So I need to draw a lot of more circles. I'm not being too particular about this. And do you notice what's happening?
They're getting increased.
They're getting what increased?
Their particles is increased.
Okay, I probably haven't drawn this very well. Let's say I remove all of these guys. And make one large guy over here. And I remove all of these guys. And make one large over here. Now, what's happening is the regular arrangement, right, of the rows of particles in a metal is disturbed because of the larger particles. This is an alloy. This is a pure metal, right? This is the regular arrangement. And then you've got these large particles that are disrupting the regular arrangement. Now remember we talked about metals being malleable, right? So they can be hammered into shapes or sheets. And so metals are malleable because these sheets of their particles can slide over one another. But what happens because of this guy, right? And right, the particles of the material that you added to make the alloy, right? They prevent, right, the movement of the particles of the metal, the movement of metal particles. And so you've reduced, if not completely taken away, the malleability, and that's what ends up making it stronger or harder, depending.
Like,
Does that make sense?
no, it is disrupting the regular arrangement of the metal. No?
Yes,
Then how it making it
yes,
more stronger?
yes. And the same thing goes with the ductility. So metals are also ductile. They can be drawn into wires or, you know, threads or strings, right? Strings of metals are called wires. And so the same thing goes, right? You're reducing the ductility of the metal. Make sense?
Yeah.
Sophia?
Yeah.
Okay. And so in your textbook, they've given you a table with, some common alloys, brass and bronze and duralumin and magnesium and solder, and which metals or metal plus non-metal, right? In this case, they're mostly just two or more than two metals mixed together. And then what is the use of those, right? So there's a table in your book. That's nice. And that brings us to the end of this chapter. Any questions?
Chapter started and ended so quick.
Huh?
Nothing.
Something?
No.
Haram, any questions?
No.
Okay. Now we're going to go back and sort of jumping around the chapters. So now we're going to go to chapter 8. Let's take a new page.
Remind me again which chapter was this again?
This was chapter 10.
Okay.
We've done chapter 9, which is the periodic table,
Yeah.
right? We just finished chapter 10. We've done chapters 1, 2, 3. So we've done 5 out of the 14 chapters.
Yeah.
Now we will begin with chapter 8. And chapter 8 is titled Acids, Bases, and Salts. So, right, the introduction of the chapter in the textbook doesn't really tell you what an acid or a base is. It comes in later. And so we're going to start with that. And that is explained with what is called the Bronsted-Lowry theory. So these two guys, Bronsted and Lowry, they are two different scientists in two different countries who about the same time proposed a theory to define what an acid and a base is, right? And what they came up with, right, for an acid,
Basics are also called alkaline. Basics are also called alkaline. No?
yes, alkali, right? So, oops, right? In fact, right, I misspelled that. It's an eel, not an I. That's a different sort of basis. I guess thanks for pointing that out. So an acid acts on acid is an H plus or proton. So we know the H plus is a proton, right? From our earlier chapters. It is a proton donor and a base is a proton acceptor. So what do acids look like? Acids look like this. You've got HCl, right? And this guy, when it's in water, it splits into the proton and right, the positive ion and the negative ion. By the way, right? The positive ion is called a cation and the negative ion is called an anion. Right? And so, right, this is what we're talking about. If it can produce the proton and that proton goes on to react with the base or something else, right? If it's able to give up, right? It's a donor, it's able to give it up, the proton, it's an acid. Another example of an acid is sulfuric acid. When you've got an aqueous solution, which means basically it's in water, it gives up two protons and the sulfate ion. And then examples of right other, so for example H2CO3, right, which is carbonic acid, or HNO3, which is nitric acid.
What is carbonic acid?
Huh?
What is carbonic acid?
Carbonic acid is the acid that you would find in your soda drinks, your fizzy pops.
Oh.
Right? And it's the carbonic acid that forms, right? So basically they pump carbon dioxide into water. The carbon dioxide reacts with the water, forms carbonic acid, and that's how you see the bubbles, the fizz in the soda. All right? You've got nitric acid and many other types of acids. Now, one thing that you would note over here, right, the nitrate, the carbon, the chloride, the sulfur, these are all non-metals. Right, so non-metals make up acids. I mean, that's not the only thing they make up, but when talking about an acid, it will be with non-metals. Okay? So these are examples of acids. What do you have for bases? Right, you've got sodium hydroxide. And again, right, when this guy is aqueous, it breaks up into the sodium ion and the hydroxide ion. Right, and this is, right, so how is this a proton acceptor? How is it a proton? Well, right, look at it this way. You've got OH minus plus H plus. What do you think you're going to get?
Negative.
Is it going to be neutral? Yeah, H2O. Exactly.
Right, so the OH is taking up, it's accepting the proton, it's forming
Negative and positive. Yeah.
that's why it's a proton acceptor.
Mm.
Right, you've got sodium hydroxide, you've got magnesium hydroxide, you've got potassium hydroxide.
So it can go with any other bases.
Go with any other bases, meaning?
Basic element, sorry, it can go with any other element for alkali, right?
I don't follow.
It can, like, basically what I'm trying to say is it can team up with other elements, right? Since it's acceptable.
What can team up with other elements?
You said that it can go with magnesium as well, and
Oh, I no, I meant examples of other bases. Like I gave you a few acids over here.
yeah.
Right, so these are examples of some of the bases. You've got sodium hydroxide, you've got magnesium hydroxide, right? Just like you had two protons being produced in sulfuric acid, you've got two hydroxide ions,
Okay.
right? So these are hydrogen ions and these are hydroxide ions.
Okay.
Okay,
Yeah.
you've got calcium hydroxide, so CaOH2. Again, it will be similar, so Ca, sorry, these guys 2 plus 2 OH minus, right? And you notice that all the, you've got the hydroxide ion, which is what defines the base, right? So the proton is the hydrogen ion, which what makes the acid an acid, and right, the hydroxide ion is what makes a base or an alkali an alkene. But what you noticed over here is it was all non-metals forming acids. Over here you notice they're all metals. Right, sodium's a metal, magnesium's a metal, calcium's a metal. Right?
Yeah.
Yeah.
Okay. Now, what is the strength of acids and bases? And that depends, right? First of all, right? It's relative. Right? And so you have to compare two or more, at least two, acids or bases with each other. Now remember, right, to understand the strength of these guys, you will be comparing one acid to another. You will not be comparing an acid to a base because they're two different things. Right? And what you will see is, right, how many molecules
The
molecules
bases are, sorry,
uh, uh, what were you saying?
the bases are usually non-metallic,
Bases are metallic. Sodium, magnesium, calcium, potassium.
and the acids are non-metal metals.
Yes, they're made with non-metals. Okay, so what you're going to look at is how many molecules of the acid or base dissociates or ionizes when dissolved in water. What does that mean? Meaning, will this happen? Will this happen when you put it into water? Right? So you've got HCl in water. right, it readily breaks up and almost completely, right, the ion. Remember, this is a covalent thing, right? So I think that might confuse you, but HCl in terms of bonding is a covalent molecule, right? But it is a polar covalent molecule.
What is covalent bonding?
Covalent bonding is when, right, two atoms share electrons.
Oh, just like NaCl.
NaCl is ionic. Ionic bonding is not sharing electrons, it is the transfer of electrons.
Oh,
Right? Sodium gives its electron to calcium. Gives it. Over here you can see that they're sharing.
yeah.
Right? But it's a polar covalent molecule. Why is it a polar covalent molecule? Because chlorine has, right, what you call it? Right? It has more protons. And so that pulls this electron pair towards chlorine, and so that chlorine develops a slight negative charge. And because of that, the hydrogen develops a slight positive charge, even though it's
Negative.
covalent, right? So we say that delta positive and delta negative, right? And because of that, when you dissolve this guy in water, it's an aqueous solution, the ions completely separate, they break up, right? So different acids work differently, right? Very strong acids such as hydrochloric acid, right, they completely dissociate into their ions, right, nothing's left. Similarly, right, I showed you hydrochloric acid, H2SO4, aqueous, right, when you put it into water, aqueous, it's already in water, it's going to give you two protons and the sulfate ion, two minus, right, and all of the molecules are going to split up, they're going to ionize or dissociate into the ions, right, and giving up their, having their protons ready for, a reaction if that happens, right. Whereas what happens with a weak acid, so these guys are strong acids, and so if I just write that down, it completely dissociates. Strong acids dissociate in aqueous solution. Then you've got weak acids. What's an example of a weak acid? Ethanoic acid, right? That's an organic acid. We'll come across this guy later. So you've got CH3COOH, right? And it's aqueous. This guy is ethanoic acid. And what you get is the proton or the hydrogen ion and this guy, right? The ethanoate ions. And the hydrogen ion. Now, what you need to know over here, first of all, the number of molecules of ethanoic acid that actually dissociate is low, right? So few molecules dissociate. That's the first point. And secondly, notice this guy, right? This dissociation is reversible, right? Meaning they can go back to forming, right, the full ethanoic acid molecule. Right? So other examples of weak acids are carbonic acid, citric acid, right? Ascorbic acid, that's vitamin C. And so a weak acid is one that only partially dissociates in aqueous solution, right? Only partially dissociates in aqueous solution. Any questions?
No.
Okay. Now, strong acids, the solutions of strong acids, right? They are good conductors of electricity. What else? They react quickly with metals, bases, and metal carbonates. And when, right, strong acids are neutralized, we'll talk about that, by strong alkali. Right, so for example, strong acid is HCl and a strong alkali is NaOH. So, right, this happens. Acid and the alkali gives you, this is neutralization. All right.
Yes. Yes.
Okay. And what else do we have? For weak, for solutions of weak acids, huh, what do we have for solutions of weak acids? right? They are poor conductors or poorer comparatively, poorer conductors of electricity, right? And they react more slowly, right? So they have slow reactions with metals, bases, and metal carbonates. Now, whether it's a strong acid or weak acid, right? All acids, in as we've seen in aqueous solution, produce the hydrogen ion, right? So the strength of, right, strength of an acid means how easily it dissociates, which we just covered. But there's also something called the concentration of an acid. Which basically means how many acid molecules there are in solution compared to the water molecules. That would mean if the molecules of the acid are more than the molecules of water, right, it is concentrated. If it's less than the molecules of water, it is dilute. And then also how concentrated or how dilute, so that's a different topic. But right, even if you have a dilute strong acid, for example, right? Let's put it this way. A strong acid is still strong even when dilute. Why? Because however many there are in that solution, they're going to completely dissociate. That's what makes it strong. And a weak acid is still weak, even when concentrated. Why? Again, the dissociation, right? They will not dissociate readily. Concentration just means that there's more of the acid molecules as compared to the water molecules in that solution. Any questions?
No?
Oh, Indonesian. Okay.
Yeah, definitely.
Right, so we've already talked about neutralization, but just there is a short piece over
Oh,
there. So,
sir,
yeah,
which ones are more dangerous? Is it like the basics or the acids?
both depending on whether they are strong or weak or whether they're dilute or concentrated. Really depends. And dangerous in what sense? Are you going to drink hydrochloric acid? Don't do that, even if it's dilute, right? Carbonic acid, well, it's a weak acid, and you do drink it in dilute form when you're drinking your sodas, right? You do consume acids when you're having grapes or citrus fruits or other foods and vegetables, right? The tangy feeling in citrus fruits like oranges, and sometimes the sour taste in grapes or other sour fruits, those are all acids, right? But they're not going to harm you because they're weak acids.
Do we consume bases as well?
Uh, that's a good question. Let me check. Just give me a sec.
Okay.
Right. So to answer your question, you have fruits such as bananas, right? Leafy greens such as cucumbers. You've got your legumes, so chickpeas and lentils, right? Some nuts and seeds, and so right, they are alkaline, right?
But these would be weak bases, no?
Hmm?
But these would be weak bases, no? 'Cause
What basis?
other than
Weak. Yeah. I mean,
yeah,
right, either weak or not concentrated. Of course, everything needs to be taken in moderation, right? So if you're consuming too much of a single food item, then whatever nutrients it contains, obviously you're piling that up in your digestive system and it could have an adverse effect, right? So even if, right, it's not exactly weak, so it's not going to be super strong, but right, it's going to be a very small quantity of it, right? Enough for your body to handle. Unless you're going to eat like 2 or 3 kilos of cucumbers, and that's a different matter.
okay.
Okay, so let's quickly go through neutralization. We already talked about neutralization. Neutralization is when you, right, react an acid with a base, and that results in the formation of a salt and water. So reaction of acid with base giving you water and a salt, right? Salt as in chemical terms. So for example, right, you've got again hydrochloric acid, you already done this, and sodium hydroxide. What are you getting? You're getting sodium chloride and water. We've got HCl, aqueous, NaOH, aqueous, right? You're getting NaCl in this case, also aqueous, and water, obviously, which is a liquid, right? And so a neutralization reaction occurs between an acid and a base to produce water, right? This is the main
Like
concept.
acid or any acid would work.
Well, normally to neutralize a strong acid, you need a strong base and similar quantities. So there's a working for that. That will come in chapter 4, which is stoichiometry, which I have not covered. I'm leaving that for later. Okay.
Yeah.
Right. So normally you would neutralize a strong acid with a strong base, a weak acid with a weak base. If you're going to try and neutralize a strong acid with a weak base, you will need much more of the weak base. If you're going to try and neutralize a weak acid with a strong base, then you will need little of the strong base to neutralize the thing, right? So something like that. Now, if we write out the ionic equation for the whole thing, right? So what we have is we have H plus.
By the way, sir, the meeting will end at in 3 minutes.
No way.
Yeah.
Okay. Unfortunately, then I will have to stop, and we'll continue from here tomorrow.
Okay, inshallah.
All right.
Yeah.
Yeah.
All right. See you guys tomorrow then. Inshallah.
Inshallah. Okay. Allah Hafiz.
Allah.
Yes.